I kind of like this article. Well, kind of, you know, in a weird sense. That is right. How did it go on? What's that thing that's screwing me up? You see what that guy says? Something about irradiating babies or something, right? What caught my eye, other than the fact that babies shouldn't be over-radiated, jeez, right? I guess in 2011, whoever monitors these things are finding out that these MRIs, they're not calibrating them right. Why am I not turning on the back lights? There they go. They weren't calibrating them right, so they're over-radiating. So not good. All right. So calibration is really important because you get numbers, but they don't mean anything if you didn't calibrate correctly. So that's where we're at. There's another article in there too, but let's talk about calibration. Pretty much the mathematics that's going on inside that computer that you don't see when they were calibrating that MRI machine. Okay, they want such a dose. Well, they were messing up when they did it. The method of least squares. Cat, the method of least squares finds the best blank blank through data that's theoretically supposed to be something. What's the second part? Linear. Got that one right. Oh, yeah. I think there's a lot of ways to fit that. But it has to be two blanks, though. So fit is right, but it doesn't fit two words. The best straight line. The best straight line. So really, I should probably reword that. The method of least squares finds the equation for the best straight line. That's what it really should say. Finds the equation for the best straight line through data. That's supposed to be linear. So, well, Erica, that leaves, what's the equation for a straight line? Yeah, y, I should write it over here. Y equals mx plus b. So what's, Jamesa, what's little m? The slope. Everybody, what's little b? Y-intercept, yeah, wherever it crosses the y-axis. Okay. If a least squares analysis is performed on your data, I guess, Amanda, you plug in all the data, push the button, it does a least squares analysis. What am I picking on, Amanda? Amanda? What does it give you? Gives you a slope and a y-intercept. It gives you a slope and a y-intercept. It gives you what the little m and the little b are, right? Because then you can plug in, think of it this way. Think of y as that MRI exposure, right? Think of the y as that MRI exposure. The x could be the time, right? So if you know little m and b, according to the computer, it knows the little m and b. You plug in, okay, this little baby, he can only have 3.5 seconds according to his weight and height. So you put in 3.5 seconds, the little regression equation kicks out the amount of radiation that kid can handle. Okay, but if it's not calibrated right, look at the danger you're going to do, right? You'd have no clue. Oh, I'm going to expose this guy 2 minutes. You don't know. So that, I'm sure you don't see the damage either. It's at the cellular level. Okay, so that's the idea. If a least squares and okay, where do you got that one? Oh, what is it used for? I kind of said that, right? So then you can predict or use it to control your whatever process it is, or to find out an unknown. That's what we're going to be doing. But you can plug in the, what's the word for this? We should probably use the right word. You can plug in the what variable? The x, but we're supposed to call it the what variable? The independent variable. Plug in the independent variable, and you get what it thinks is going to be the dependent variable. If you calibrate it right, it'll be right too. If you calibrate it correctly. Okay, give it good data, you'll get a good regression equation. Assuming things are linear in the first place. If it's not linear, you don't do this, right? And that could be the case with that MRI machine. It may not be a linear relationship between time and exposure. So, assumptions in least squares analysis. Delta y is bigger than delta x. What does that probably mean? Adriana, what do you think that means? Maybe you've seen this sometimes. Have you guys ever seen this? And you have a plot, and then they have this guy, all right, or this guy, little dinky ones, or they had it the other way. What are those? What are they trying to show? Yeah, a lot of ways you could explain it. The variation, the standard deviation, the uncertainty. Remember the plus minus story? Well, the plus minus in which direction just better be bigger. The uncertainty had better be bigger in which range, the x or the y, for this to work correctly. The y. They don't want, for this to work right, you don't want much uncertainty in the independent variable. You want it to all go with the dependent variable. And then you want all these uncertainties to be about the same, regardless of what the y is in your calibration range anyway. So I don't know how well applicable those are, but you know, if it comes to life or death or exposure, I think they should probably understand that actually is true, right? Does their machine, what this is saying is, think of that y. If that's the MRI exposure, at really high, after long periods of time, maybe that stinking little, a lot of light bulbs are this way. MRI is much more complicated. I'm saying electronics. Don't things warm up? Don't things glow a little bit better, a light bulb, if it's been warmed up a little bit? Fluorescent lighting, perfectly. Maybe that MRI machine kicks out more juice the second hour it's been on. Or the second, if you want a 30-second exposure, maybe that last 15 seconds is bigger than the first 15 seconds. You know what I'm saying? You don't want that delta y to be big. You want that to be bigger than the delta x. But the machine's got to know all this. Okay, and if that's a problem, this won't even work, least squares. Yes?
Why did you put 2 graders?
Oh! No, I'm glad you noticed that. Okay, these mathematicians are all big about notation, about using the least language possible. In fact, they use no language. They use greater than greater than. What does it mean? 1 greater than means greater than. Greater than means really, really greater than. That's what it, thank you for noticing that. It's not a typo. It just means much, much, much bigger. They don't want it just bigger. It has to be much, much, much bigger. Okay, we have a straight line, y equals mx plus b. Now this works only if you plot what versus what, you'll get a straight line. What do you plot? And y equals mx plus b. You have to plot what versus what. What up here? Y. And down here you plot x. So you plot y, you plot x. Your slope, everybody, would be little m, and there's our y-intercept. Okay. It doesn't have to be y equals mx plus b. There's linear relationships all over the place. It just depends on how you plot things. But take a closer look at what we just did. If you plot y versus something else, you notice whatever you're multiplying by the independent variable, that's going to be your what? Slope. Okay. Here's a hint. This is kind of an easier one. Let's plot, I don't know. Well, you tell me. What could you plot, what versus what, and get expect a linear relationship? This is what's going on in the physical world. You could plot what versus what, and you better theoretically get a linear plot. What could? Okay, plot. What do you want to put on the independent? You can put time. There's nothing wrong. You can put any of them down there. Just that time's an easier one to see. Time and Which one? VF. All right? Because if you put VF here, it's really easy to see that this is going to be your y-intercept. All right? Now that was kind of an easier one. That was kind of easy. This one, though, I don't know if you recognize this. Does anyone remember this from physics? This is the distance that something falls on planet Earth, because that's what our gravity is. And t is the time squared, right? The time that it fell. Okay. What could you plot here and expect to see a straight line? Okay, let's try that one. If you plotted distance versus time, right? You have this data. You have the distance. You measure the time. You plot it out. It's not straight. It's parabolic. That ain't going to work. Distance versus... Because now, let's back up a little. You're right, but let's back up a little bit. If we said time, what's really... Because go back to here. Whatever you're plotting it against, whatever you're multiplying it by is the slope, right? If you did t, what's really out front? 1/2 g times t. You're plotting 1/2 gt. Sorry, your slope is 1/2 gt. Is t changing? Yeah, so your slope is going to be changing. A straight line is how many slopes? Just one. You can't change your slope. Okay, that's why it's a straight line. So what would be down here then? T squared. Yeah, someone said t squared. So your slope would be what then? What would be your slope? We're going to plot d versus t squared. What's out front? 1/2 g. That would be your slope. What would be your y-intercept? 0. It's going to go through 0 on the y-axis. Okay. How about this one? F equals ma. Plot force versus, just pick one. You can pick acceleration, I don't care. Your slope is going to be mass. Your y-intercept would be? Y-intercept would be 0. All right, if you really know what's going on, if you can do this one. Okay. Definitely you want what on your y-axis, otherwise we're going to have to do some algebra. Definitely put force there, right? Okay. There's no right or wrong answer here. I mean, there is right or wrong. I'm just saying, pick out a linear relationship, and there's a lot of them. All I want us to do is start picking some out. What could you plot? What versus what? And you should, in theory, get a straight line. I don't know what M and D and C are. Just make them up. Plot what down here? Plot m squared would be the possibility, because then your slope would be 6. Y-intercept would be 48d over c. That's assuming d and c are constants or something, right? You could do that. What else could you plot down here? F versus d. You could plot F versus d. Nothing wrong with it. Then your slope would be what? 48 over c. Y-intercept 6 over m. Right? That's the game you're playing. So every equation has linear relationships. You just have to pick them out and make them fit y equals mx plus b. Okay. So calibration curves. So we have some really dangerous stuff. It's called chemical blue. And it just kills you if it's get a little micro drop on you. Okay? And then we have this unknown bottle of this chemical blue. And we got this stock solution of chemical blue. Now this stuff, it won't kill you if it's below like 0.1 molar. This is 11.7 molar. It won't kill you if it's less than 0.1 molar. For some reason, theatrical dudes, what do they call little troops, right? They really love this color. They want to use it in their theater show, right? So it's up to you, man. I don't know why they have to be this color, but it does. So if you screw up, the guy in the theater, right? Okay. Is this good enough? What do? You make a calibration curve. So we need data. What data do you need? Well, let's get some data here. Probably the concentration of the blue would be good, right? And then we need some instrument. Now this signals of stuff, that's an entirely different course. There's so many things that go into it that it course on its own, so don't really worry about it. You're going to put it in the machine, a black box, and you get a number out. And the more stuff there is, the bigger the number. Okay, so how do I, well, here's one of them. I know this guy's concentration, 11.7. So I could put him in the machine, right? And measure his signal, whatever it is, and get a dot. All right, so this would be signal. And this would be the concentration of my blue. But how would I need more dots. Because it's supposed to be a calibration curve. So how would I make more dots? Knowing if I had this stuff, can you see all this stuff? Dilutions. What's the equation you'd have to use? Mi Vi equals Mf Vf. So you pick a concentration you want to make. I want to make, that 0.1 is really important, right? That's the one where they die. So we definitely want to have that in there, right? And you just pick right on a whole bunch of them. Right? Maybe you can list them high to low. Make a 5, a 0.1, a 0.01 maybe. I don't know, I'm just making a bunch up. But how would you make one of those concentrations? MIVI equals MFVF. 11.7 would be your MI, right? And the 5 molar would be my MF. And the VF would be, just depends what size flask you grab, right? Well, I'm going to grab this flask, so this would be my VF, 100 milliliters. And my VI, you do the math, MIVI equals MFVF, you calculate it. Okay, it's 2.3 milliliters. Okay, well then, take 2.3 mils of it, put it in here, fill it up to the mark, stir it up real good. Probably want to wear gloves and stuff, since it'll kill you. Then it's 5 molar, definitely kill you. And then you measure all this stuff. Okay, so you get a bunch of data. Plot it all out. It's not going to be perfectly linear, but it should be close. Okay. So why linear? Why is that? I mean, it doesn't have to be. Depending on the machine or, yeah, depending on the machine, it might start looking something like, right? But why is linear better? Why are linear calibration curves preferred? Not all of them are, but why would it be easier? The slope's constant. Look at all the look at all the dots. You need a lot more data points to characterize that curve. I mean, just get rid of one. It looks linear now, but it's not linear if you got more data. So if it's not linear relationship, you're sitting up in lab all day getting dots, especially for something as important as this. But if it's linear, come on, 2 dots is probably good enough, but you should get more so that it shows the other guys are good, right? So, and you know if you're way off. If it's linear and you measure one, it's way up there, oh man, he's messed up. I got to do him again. But that doesn't work on curve. Okay, so linear is a lot easier to mess with. Calibration curve is done. How do we use it to get the concentration of this? Oh yeah, we got to get it signal. Good. So we're going to measure our signal here of our unknown. It's going to be some number. Then how do we get this? Yes. Now you can use our nice little plot. Right? You can use a nice little plot. But come on, guys, don't you like making these plots? They take forever. And then if you do Excel and you print it out, you use a ruler and, okay, this is the signal, I'm going to go down, and right? That's what you'd have to do. That is not the way to do it. You do a what analysis? What do we call it? Linear regression analysis. Get your little m, get your little b, calculate it, right? Because if you're not comfortable with it, you're plotting signal versus blue. This is my y. This is my x. Y equals mx plus b. That's my signal. That's my concentration of blue. So you just plug in those numbers. You plug in the number for the signal for the unknown. Calculate it. Calculate the concentration of the blue. That's the way to do it. Plotting it out is just, no. Okay. So you do that. You get the signal, and let's say the lowest one you had, right? Kind of talking about this one right now. The lowest signal you had, that you made for your standards, is I don't know, 0.89 is your signal. But you measure your unknown, and you get 0.58. Right? This is you drew your best straight line through there, but you get 0.58 for your signal, for your unknown. What do you do? Right? Well, if the signal for your unknown is above or below, in this case it's below. Casey, any idea? What should we do? I mean, it's linear. Yeah, we measured again. That's still 0.56. We could just get a ruler out and draw another line, or we could just kind of use our same equation, assume that it's linear. If you use the same equation, what you're saying, right? Here's our calibration curve data points. If you use that same linear regression equation and just plug in the 0.56 for signal and calculate it, what you're saying is that this guy is going straight. Did you prove that? Are you going to bet someone's life on that? No. You have to make a standard below 0.56, put it on the plot so it's involved in the regression analysis. That's the only way to verify it. Because a lot of funky things happen with these instruments in this course, especially up here at high concentrations. But down here they could. The actual response could level off instead of being linear. You don't know. Funky things happen at different concentrations. You have to make an unknown. Your standards always have to border. You have to have at least one standard above and at least one standard below your unknown. You have to. Otherwise, it's just not. Otherwise, this kind of thing could happen. Well, you radiate some babies a little too much. Okay. So that all works handy-dandy for something like this. The solvent is this, pure water. Works great. What if, though, I don't know, I hired somebody in the lab, and man, how do we get rid of this blue? All these theater guys, they're done with it. We go out to Elmendorf, right? You can't dump it out there. City comes back, you just dump blue in Elmendorf. Little fishies, little turtles. Your argument is, hey, oh, come on, the concentration's way too low. Well, the point is, what you did was illegal, but the point is, what's the concentration in this Elmendorf water of, where's my blue, of this stuff? Do you see the problem of making a calibration curve now? Okay, we'll filter it. We'll get all the little greeny specks out of there, and the twigs, because that's not the blue. But it might be, so you might, wow. Assume that the blue didn't attach itself to there. There's problems because this is not pure water. This is a bunch of stuff in there. And you got to understand what your machine's doing. What if your machine is detecting some little signal that it's also in here, like copper? Copper has a bluish color to it. I'm sure there's copper in this water. So, you're going to get signals that are off. How do you handle it? Standard addition technique is the best thing that we have to handle it. It's the most straightforward, too. the idea really helps if you understand what a matrix is, your sample matrix. Here in this unknown for the theater study, the sample matrix was just pure water, right? It's just the matrix is everything that's surrounding the analyte. What's the analyte? The analyte is what you're after. Because there's a lot of stuff could be dissolved. It's what you're after is the analyte. And for example, up here, our analyte is the blue killer, the blue carcinogen, the blue chemical. So analyte is what you're after. The compound the compound of interest. There could be a lot of compounds. Okay. So the matrix is just in the chemical environment everything that's surrounding that analyte. So in this case, it's just water. It's really easy to reproduce that sample matrix. But here, it's not so easy to reproduce that sample matrix. So what we're going to do is we're going to cheat. You could reproduce this. In other words, you'd have to spend a good amount of time, probably get a PhD out of it, figuring out what the heck is all in here. And then you dump it all in a container, and you'd have it. And you could reproduce that sample matrix and use that instead of water, right? And just do the whole MIVI, MFVF thing, and just use that sample matrix you made as the solvent. Because you got tons of it. You made it. You ain't going to do that. It's way too much work. But standard addition technique is really that, though. We're going to use this as the solvent. We're going to use this. And it's just going to cancel itself out. Let's see how. So here's your unknown solution. That's the Elmendorf stuff. We need to have a stock solution. You need to know what your analyte is. No problem. We have a bunch of it right here. Here's our analyte. And we know its concentration. It's nice and concentrated, just what the standard addition technique wants. It wants a concentrated solution of that analyte that we're after. So that's what CSTD stands for. Concentration of the standard. Concentration of the analyte, what you're after. Okay. C-UNC probably means the concentration of the unknown, right? That's the Elmendorf stuff. Okay. So look what they did here. They took 4 containers, 4 volumetric flasks. Here they are. They took 4 volumetric flasks. And what did they do? I like the color coding here. V-UNC. Looks like it's the same volume of in each. So, what's my unknown? This is my unknown. I take probably 10 mils. Doesn't really matter. Take 10 mils and put it in this one. Take 10 mils of the Elmendorf, put it in that one. Right? That's what they're doing. They took the same volume. That's what's key, though. Take the same volume and put it in each one. Okay? So I have my unknown in there now, in the same amount in each flask. Then what they do? And then what's next? VSTD? Volume of the standard. So did they take the same amount and put it in each one? No. In fact, in one, they didn't put any at all. They put none in there. They put no standard in this one. And they wrote down these volumes. They put a known amount in there, and then slowly increased it. Okay? And then they bumped it up to the mark. Okay, with water or something, probably. Pretty much whatever, just so that things mix. It doesn't really matter what the solvent is. Okay, then they mix it up really, really good. Then they made a plot. Again, you have to get some instrument, some machine, that'll give you a response for your unknown. Since it's blue, I would just use UV Vis, right? It's blue. Except just think, imagining blue in this. But realize you have the same amount of Elmendorf in every single one of these. So if this absorbs blue, this absorbs blue, this guy's going to get canceled out because he's in every one of these, right? This unknown. So that signal's going to get bumped up the same amount in each one. But they're going to get bumped up even higher for the guys who have more unknown in there, more standard. So you can get your biggest signal here and your lowest signal here, right? Because you have the least analyte. And then you plot it. Okay. plot your signal that you get versus the volume of standard that you added in there. And remember, one of them had 0. So one of these guys is 0. And then you plot it out. And then you do a what analysis? It's linear. Do a linear regression analysis. So you get your little m and your little b. You get your m and your b, right? They pop up when you do a regression analysis. So you plug those guys in. What was v unc? The volume of the unknown that you put in each one of those. You put that in, divide that in the denominator. CSTD was the concentration of the standard, whatever concentration you used of that standard. And then you'll calculate C unc, the concentration in the unknown. Okay? You'll know what the concentration is of that unknown in that original Elmendorf stuff. Okay? It all comes out in the math. So that was standard addition technique. We didn't use the word, did we? External standard? This was called, when we did the blue dye, and when we did MIVI, MFVF, and put it in each one of those, and remember we made this nice little table. They call that the external standard technique. Because you're making all these standards and just plotting them out, getting a calibration curve. It's called the external standard technique. But when you can't easily reproduce your, what was it called, the M word? When you can't make the matrix, do the standard addition technique. Okay. I think this is our last one we're going to talk about. Gases are difficult to sample reproducibly because sampling fluctuations are a common occurrence. The reason why this is a big deal try to get more dots in this one. All right, there's more dots in number 2 than there is in number 1. What does GC stand for? Does anybody know? Gas chromatography. You might have heard of it, but you learn about it backwards and forwards in Chem 3422. But the point is, when you're sampling a gas, this happens all the time. It's really hard to get the same number of molecules, right, the same amount of sample every time you sample a gas. It's going all over the place, right? It's really hard to sample it. And this is fine. The problem is you get a bigger signal. But I just sampled the same thing twice. How can I get a bigger signal? Right? So it's messed up. So what they do is they add an internal standard. Now, how does this work? All I'm saying is I got to change colors. An internal standard. My internal standard is going to be purple. Okay? So I just added it to my unknown that I'm analyzing on this instrument. I added this internal standard to it. So I sample some. If my machine samples too much, don't I also sample too much internal standard? Yeah, so I have to add more dots. I added 3 that time, so I better add, I don't know, something like that, right? So what didn't change? What can you measure to reflect no change at all? Before we just measured signal. You remember that? You just plotted signal, and it could be versus concentration or something, and you're hoping to get this nice straight line, okay? But if you plot signal of your analyte divided by signal of the, does anyone see it? Internal standard. Because if you just plot signal of the analyte, sometimes it's going to be too big. But you're doing the same thing twice. But it's just sample fluctuations. You can't control it. So if you instead plot signal of the analyte versus signal of the internal standard, signal the internal standard, It's a little more work, right? You have to measure the signal of two things, but you get a perfectly straight line, regardless of your sampling fluctuations. It solves it completely. So if you ever hear GC, you can really sound smart by saying, did you use a what standard? Internal standard, right? And not really have a clue what's going on, but man, they'll say, yeah, we did. Or no, we didn't. And you can say, well, why didn't you? Sampling fluctuations are going to get you, right? That will work every single time. Okay. So, like I said, the internal standards, if you want to do quantitative analysis. What's a quantitative analysis? Numbers. You want the amount of something. That's all we're talking about are quantitative analyses. Versus what type of analysis? Qualitative. You want to know what it is. Now, that's something else. Okay, here's some questions. Suppose you carry out an analytical procedure to generate a calibration curve like that shown here. Okay. So you're getting a bunch of data. And you measure your unknown, right? Because you want to get an absorbance of it. So you did all this work. You measured your absorbance, and you had your concentration of your. Well, how do you write concentration? CON, CEN. And you measure your concentration of a bunch of standards. Right? You measure all that stuff out. You did all this work. You plotted it out. You got your little m. You got your little b. Right? And then the last step, you put in your unknown. All ready to go. You get a negative number. How the heck can you get a negative number? What is absorbance? Does anybody know? It's kind of like, oh, this is really all you need to know. Which one has a higher absorbance of blue? Which one is, yeah, he's darker. He's absorbing more. Actually, he's absorbing more. What's a complementary color of blue? Is it red? Is it red? So he's absorbing more red than he is all. Really, right? He's absorbing more. So you put your unknown in, you get a negative number. No one's had instrumental in here, right? Can't pick on. Natalie, you haven't had instrumental? You haven't had. I thought you. No one has. So I can't pick on anybody then. Okay. What happens is that you pretty much have to see the math. I'm sorry about this because you don't really need to know it, but absorbance is really two measurements. You have your little, what do you call it? It starts with a C. You put it in the little instrument. You dump your stuff in there. Cuvette. You have your little cuvette, right? And it has some incident light, and then it has the light that got through. Okay? And if you're going to measure, if you're going to get negative absorbance, it just means that your background is absorbing too much. It means that the only way that it can really make sense is if you actually, like a little spec 20. Do you ever use a spec 20? Hey, you put them in those little cuvettes and you write down the absorbance. Okay, so let's say you have your little cuvette, you fill it with water, and you put it in there, and then then you take it out and you fill your cuvette with all the little things you want to put in. Right? You write down the absorbance. With me so far? Okay, you've done that. Now, the reason why you had to put the water in there all by itself in the first place is to get the background. The background. Because the absorbance is really two measurements, one over the other. So what if you did this and you weren't very careful? You grabbed a cuvette. I don't know. What could you smudge on there? You guys use lotion or something, right? Yeah, you didn't. You didn't make the sides clear. You just put on a bunch of makeup or something, right? Or you kissed your cuvette. You kissed your cuvette for luck. That's what you did. You kissed your cuvette for luck, right? And you had this big red smudge on there. Now, this is the cuvette that you're supposed to put in there that's nice and clear, right? That you put in at the beginning for your water. You kiss it for luck. You want your whole analysis, right? You can do all your measurements after this. So you kiss it for luck, put it in there, and I did your background thing button, and then you took it out, and then you filled the cuvette with all the other stuff you're supposed to measure. But you didn't kiss those guys. The absorbance for that initial one you put in is higher than it is for the stuff that you're trying to measure. When your background is too high, you get negative absorbance. It just means you screwed up in your background. Okay? That's what it means. I don't know if that helps you or not, but it's a homework question, so I thought we should talk about it. But this is more like a quiz question right here, I think. Using the calibration curve in figure 4-11, find the quantity of unknown protein that gives a measured absorbance of 0.264 when a blank has an absorbance of 0.095. So we better figure out what the heck this figure 4-11 is doing. All right? Let's take a, we need, all right? Okay. Where is some stuff? Here it is. We need that. Oh, we're about out of time. But you've done this. Y equals mx plus b. But it makes more sense if instead of writing y, you write absorbance. Right? Write your absorbance. Equals m. Put in the number for the m. The x is amount of protein, right?
X is the amount of protein.
Well, I didn't. The figure did. Right? Look what's on the x-axis. Plus my little b. Now, where do you get these numbers? Yeah, it's up here. Right? They have it up there in the reading. So you can, if they give you an absorbance, you calculate the amount of protein. Right? As long as you know what little m and little b are. That's all the questions involved. Okay? So give it a shot. Come by. I'll be glad to help you out.
You were saying right here, the absorbance